Hello everyone, I Aarti Bajaj, faculty in MCA department from Technia Institute of Advanced Studies. Today I am going to deliver a lecture on digital logic circuits. Digital logic circuits, it form the basis of any digital system. Digital logic circuits, it divided into two combinational circuits. One is the combination logic, another is the sequential logic circuits. These circuits can be easily analyzed and designed using the Boolean algebra, which is the mathematics associated with the binary system. How combinational logic circuits can be designed and used for interesting practical problems that we will discuss later on. So, the learning objectives of today's lecture are to understand the basic terminologies, types of logic gates, the AND, OR, NOT, NAND, NOR and XOR, to understand the basic operations used in computers and other digital systems. The third objective is basic rules of Boolean algebra, De Morgan law, and the final is universality of NAND and NOR gates. So, first of all, we will discuss about analog and digital signals. The analog, the circuit that we have considered so far process analog signals, in which the signals like varies continuously with respect to the time that the amplitude can take of any value. So, with the advent of the digital computers, another type is the digital signals. It is popular. In using the digital signals, we sample the analog signals at various instants and convert the continuous analog into the discrete numbers. So, this is done by a so-called analog to digital converter, which is also called the ADC circuit. The digital signals can only take on values within a finite set of numbers. For example, an analog voltage signals, it may vary continuously within 0 to 50 volts. However, a digital meter may display only voltage values instead of 1 volt. Most commonly used digital signals are binary in nature, that is, they can take on one of two values, 0 and 1. The numbers 0 and 1 are represented by two voltage in a circuit. For example, 0 can be represented as 0 volt and 1 can be represented as 5 volts. So, after discussing the analog and digital circuits, now we will discuss the advantages of digital systems over the analog systems. Digital systems, these are extensively used for most practical applications in our modern world. They have the advantages of greater flexibility in terms of computation, ease of designing using simple reusable building blocks and greater precision. So, after discussing this, our next topic is Boolean algebra. Boolean algebra with the help of logic gates. Boolean algebra, defined by the George Boole, is the mathematics of digital logic and is useful in dealing with binary system of numbers. Boolean algebra is used in the analysis and synthesis of logical expressions. These are constructed using logical variables and operators. The value of any logical expression boils down to any of the two logical constants like the true and the false. In Boolean algebra, a variable x may take any one of the two possible values, either 1 or 0. So, it may represent it like either the true or false, which is the truth or the falsehood of a statement, on or off of a switch, and high such as 5 volt and low such as 0 volt of a voltage level. So, this is the Boolean algebra in terms for representing 0 and 1, as all of you know. Now, the electrical circuits designed to represent logical expressions are popularly known as logic circuits. Such circuits are extensively used in industrial process, the household appliances, the computers, the communication devices, the traffic signals and microprocessors to make important logical decisions. Now, the logic circuits are represented by the logic operations involving the Boolean variables. There are basically three basic logic operations. These are OR operation, AND operation and the NOT operation. So, we will illustrate the three operations AND, OR and NOT using the different Boolean variables A, B and C. A, A logic gate is an electronic circuit which makes the logical decisions based on these operations. So the logic gates have one or more inputs, like A and B, two inputs are there, and it will gives only the one output, like C is the output. So the output which is active only for the certain input combinations. So the logic gates are the building blocks of any digital circuit. Logic gates are also called the switches because it contains the on-off state. With the advent of the integrated circuits, the switches have been replaced by the TTL. TTL is your transistor logic circuits and the CMOS circuits. So first is our AND operation, and which defines the C is equals to A dot B. A dot B means we will multiply two inputs and it will gives us a output. So for all the combination of input variables values like the A and B, thus in an AND operation the output will be only 1. It will be true only if and only the inputs are true. So it is clear to all that the output C, it will be only 1 at that time when both the inputs will be 1. So following relationships which can be easily derived using the circuits like A dot A equals to A, 1 dot A equals to A, 0 dot A equals to 0, because 0 multiplied by any input becomes at 0. So the multiply sign can be omitted if we indicate C equals to AB, because AB also implies the A dot B. This is the function of AND operation. The next is our OR operation. OR which is represented by the plus sign. So C equals to A plus B. For using the A, B and C, the logical variables, the plus sign represent the logical addition, which is also called the OR operation. Thus in an OR operation the output will be 1, means true if either of the input is 1, either the A is 1 or the B is 1, then it will be 1. If both the input will be 0, only then it will be 0, otherwise in every state it will be 1, because 1 add in 0 also becomes the input as 1. So the following relationships, these relationships can be easily derived using the circuit like A plus A complement equals to 1. A plus A is also 1, 0 plus A is also 1 and 1 plus A is also 1, because the input is one input is true, so the result will be true always. Third is our NOT operation. NOT operation, it is represented by the complement. So the C is equals to A complement. The NOT gate has only one input which is then inverted by the gate. For example, if it will take 1 as an input, so it will provide the 0 as output, or the vice versa. So these are the basic operations, the OR, and the NOT operations. Now after discussing these operations, we are going to discuss the multivariable logic gates. The many logic gates which can be implemented with more than 2 inputs for the reasons of the space in the circuits. Using multiple input, the complex gates are made. So you will encounter such gates in the real world. In general, AND function on n variables is 1 if and only if all its arguments are 1, or in terms of OR, the functions of n variable is 1 if and only at least one of its argument is 1. So if I am going to discuss the truth table for the AND gate which contains the 3 inputs A, B and C, so the result will be 1. It will be true only at that state when all the inputs will be 1. Otherwise the all output will be 0, because 0 multiplied by any number becomes at 0. So that's why in terms of AND gate the output will be 1 when the 3 inputs will be 1. On the other hand, in terms of OR gate, the truth table defines the output will be 1 at least when any input will be 1. But it will be 0 when all the inputs will be 0, otherwise the all results will be 1 in any terms. Next is our universal gates. Universal gates which defines the NAND gate and the NOR gate. Both are the universal gates. The first is your NAND gate. NAND gate, it combines the and the NOT operation. Both becomes to form a NAND gate, and plus NOT. in from here and from here. So it will become NAND. The logical expression forms for the NAND gate C is equals to A dot B, the complement. Complement comes from the NOT and A dot B comes from the AND gate. That's why it becomes the NAND gate. So next is your NOR gate. Similarly, it is a combination of OR and the NOT. Instead of AND, we are using OR. OR from which contains A plus B and NOT which defines the complement. So the result will be C equals to A plus B complement. Universality of the NAND gates. NAND gate can be used to implement the functions of both the NOT gate and the AND gate. Thus, any given logic function can be implemented by using the NAND gates alone. For this reason, NAND gate is said to be logically complete because it defines the properties of both the gates. And the last is your universality of the NOR gates. Likewise, the NAND gate, it can be shown that any logic function can be implemented using the NOR gate alone. This is because NOR gate can be used to implement the function of both the NOT gate and the OR gate. A NOR gate that is functionally complete because the AND, OR and NOT gates can be implemented using the single NOR gate. This is the main reason the NOR and the NAND both are called the universal gates. After this discussing the universal gates, our logic circuits is completed. So I hope that will be beneficial for you people and all of you must understand this lecture. Thank you.